Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A profound sense of disorientation permeated the world of physics in the opening years of the 20th century. The elegant, clockwork universe of Isaac Newton, a conceptual edifice that had stood for over 200 years, was suddenly beset by foundational cracks. Albert Einstein's 1905 paper on special relativity did something far more disruptive and proposed a new theory. It invalidated the very language physicists used to describe reality. The intuitive, absolute concepts of space and time, the unshakable bedrock of the classical worldview, were revealed to be contingent, observer-dependent constructs. This created an epistemological vacuum. If the most fundamental concepts of physical science were unstable, what, then, was the relationship between the scientific theory and the world it purported to describe? How could science advance with its conceptual tools dissolving in its hands? Into this intellectual maelstrom stepped a young Viennese physicist, Philipp Frank, a man uniquely prepared by his education and disposition to confront this crisis head-on. His response was immediate, pragmatic, and would lay the groundwork for a revolution in the philosophy of science itself. The central problem was one of meaning. For centuries, a physicist could speak of the length of an object or the time of an event with a sense of unambiguous certainty, assuming these quantities corresponded to some absolute underlying reality. Einstein's work, demonstrating that length contracts and time dilates depending on relative motion, shattered this comfortable correspondence. The question became urgent. If length and time lacked a fixed, intuitive meaning, how could a physicist use these words coherently? The danger was a descent into two equally perilous extremes, a retreat into untestable metaphysics, inventing invisible ethos and absolute reference frames to salvage old intuitions, or collapse into a radical skepticism, where scientific theories were seen as mere formalisms with no purchase on reality. Frank perceived that the path forward required a ruthless clarification of the link between a physical concept and a concrete world of experience. His unique methodology emerged directly from his intellectual heritage. Frank had studied physics under the great Ludwig Boltzmann, from whom he absorbed a deeply statistical and probabilistic understanding of nature, an outlook that made him comfortable with theories whose consequences defied simple, deterministic intuition. His philosophical compass, however, was set by the formidable physicist and philosopher Ernst Mach. Frank was a devoted student of Mach's positivism, a philosophy that argued with relentless force that the proper domain of science is the description of relationships between observable phenomena. For Mach, abstract concepts like atom or force were valuable mental shorthand, economical summaries of experience, and became dangerous metaphysical illusions the moment they were mistaken for unseen realities. Frank took this Machian principle and forged it into a powerful analytical tool for the new physics. He insisted that the meaning of any physical concept is entirely synonymous with a set of concrete, repeatable, physical operations used to measure it. This principle, later known as operationalism, became his scalpel for dissecting the new physics and excising its phantom limbs. A compelling illustration of Frank's method is found in his early lectures and papers delivered between 1907 and 1912, where he systematically deconstructed the concept of simultaneity. In the Newtonian world, simultaneity was absolute. If two lightning bolts struck the Earth, they either happened at the same time or they did so sequentially for all observers everywhere. The concept required no further definition. Frank, following Einstein, demonstrated that this was a hidden, unexamined assumption. In relativity, the concept of simultaneity is explicitly defined by an operational procedure. An observer in the middle of a moving train car, for example, determines if two events at opposite ends of the car are simultaneous by seeing if light signals from each event reach them at the same moment. Frank's crucial insight was to show that the so-called paradoxes of relativity were logical necessities flowing directly from this operational definition. For an observer standing on the ground watching the train pass, the light from the lightning strike at the rear of the train has a longer path to travel to reach the midpoint observer who is moving toward the front strike. Consequently, the ground observer will measure the two events as sequential. The seeming paradox that events can be simultaneous for one observer and sequential for another vanishes. It reveals itself as a direct consequence of a rigorous, operational definition of simultaneity. Frank's analysis showed that the classical view was based on a vague, metaphysical feeling of the universal now, while the relativistic view was based on a clear, communicable, and verifiable procedure. This approach stood in stark contrast to the work of contemporaries like Hendrik Lorentz, who tried to explain relativistic effects by positing physical contractions of objects moving through a mysterious, unobservable ether, a last-ditch effort to preserve a classical ontology. Frank's thinking was a powerful synthesis of the era's most potent intellectual currents. The anti-metaphysical empiricism of Ernst Mach provided the foundational principle. The statistical mechanics of Ludwig Boltzmann gave him a mental framework comfortable with counterintuitive, probabilistic outcomes. A third, crucial influence was a French mathematician and physicist Henri Poincaré. From Poincaré's conventionalism, Frank absorbed the idea that certain foundational elements of science, like the choice of Euclidean or a non-Euclidean geometry to describe space, or definitions, or conventions we choose based on their utility and simplicity. This prompted Frank to see the definitions at the heart of relativity, like the operational definition of simultaneity, as precisely these kinds of powerful, fruitful conventions. His ongoing dialogue with Albert Einstein, of course, provided the rich and revolutionary subject matter upon which he could apply these philosophical tools. Frank was among the very first to grasp the full philosophical implications of relativity, because he possessed the conceptual apparatus to see it as a new language for physics, a language built on operational clarity. This early work, articulating a clear, pragmatic, and physics-grounded philosophy, had an immediate and profound impact on the intellectual climate of Vienna. His lectures attracted a circle of thinkers who were similarly grappling with the need for a new, rigorous foundation for knowledge. Figures like the philosopher Moritz Schlick and the sociologist and economist Otto Neurath recognized in Frank's analysis of relativity a working model for their own, more expansive ambitions. This saw how Frank had successfully applied Machian principles to the most advanced and perplexing area of contemporary science, purging it of metaphysical residue and grounding it in empirical procedure. His work, was a proof of concept. It demonstrated that a philosophy could be both scientifically informed and logically rigorous, providing a powerful alternative to the speculative German idealism that still dominated continental thought. Frank's early, incisive response to the crisis of modern physics therefore became a critical catalyst, providing the concrete example and intellectual momentum that would soon coalesce into one of the 20th century's most influential philosophical movements. The stage was being set for the formal organization of the Vienna Circle, where Frank's pragmatic, physics-first perspective would become an essential anchor. The intellectual ferment that drew thinkers to Vienna's Boltzmann found in Philipp Frank a figure of unique and indispensable constitution. When Moritz Slick formally convened his now famous discussion group in 1924, he gathered logicians, mathematicians, and social scientists, all animated by a shared desire for philosophy cleansed of metaphysical ambiguity. Among these brilliant minds, Frank stood as the essential link to the living, breathing enterprise of physical science. He was a high priest of relativity and quantum theory who could descend from the abstract empyrean of tensor calculus and Hilbert spaces to speak in the concrete, operational language the circle required. His presence ensured their philosophical project would remain tethered to the very science it sought to understand. He was the group's physicist in residence, and his intellectual gravity would prove crucial in shaping the trajectory of logical empiricism, the central quandary that preoccupied the Vienna Circle in its formative years with the criterion of meaning. Their foundational commitment was to empiricism. A statement has meaning if and only if it is, in principle, verifiable for experience. This principle, sharp and effective when applied to simple propositions like the temperature in this room is 20 degrees Celsius, became profoundly problematic when confronted with the vanguard theories of modern physics. How, for instance, could one directly verify the Schrödinger wave equation? Its terms describe a probability amplitude, a complex valued function evolving in an abstract configuration space. There is no instrument that measures psi, the wave function, directly. Likewise, the statement that spacetime is curved by mass energy, a cornerstone of general relativity, resists any simple one-on-one correspondence with a single observation. The circle risked formulating a philosophy of science that, in its zeal for empirical purity, would classify its most successful contemporary theories as meaningless. Here, Frank's contribution became paramount. Drawing from his deep engagement with the actual practice of physics, he advanced a more sophisticated, holistic, and pragmatic conception of scientific meaning. He articulated what he termed Verbindungsketten, or chains of connection. According to this model, the meaning of a high-level theoretical postulate is established through an intricate network of logical and mathematical links. The Schrödinger equation, for example, acquires its empirical meaning because from it, one can mathematically derive predictions about the spectral lines of hydrogen. These predictions, in turn, are formulated as statements about the expected patterns on a photographic plate, which are, finally, the kinds of propositions that can be checked in a laboratory. The meaning of the initial equation is a function of the entire deductive chain that connects it to the world of observable facts. A theoretical statement is meaningful because it is a load-bearing element within a structure that, as a whole, makes contact with experience. This perspective placed Frank in a fascinating and productive dialogue with the other leading figures of the circle. He held the profoundest respect for Rudolf Carnap's logical genius. Carnap was attempting to construct the entire world of scientific knowledge from a minimal basis of elementary experiences, using the powerful tools of modern symbolic logic. Yet, from Frank's vantage point as a physicist, Carnap's project at times appeared to be an exercise in rational reconstruction that overlooked the messier, more intuitive and path-dependent ways scientists actually build and validate their theories. Frank's chains of connection were less a formal logical system and more a description of the functioning scientific process. Similarly, he engaged with the circle's convener, Moritz Slick, who was deeply concerned with the ultimate foundation of knowledge in direct, incorrigible moments of experience, which Slick called Konstaterungen or affirmations. For Frank, these moments were the indispensable endpoints of the chains, the points of empirical anchoring. His work, however, focused on the chain itself, the vast and complex theoretical apparatus that gives these endpoints their scientific significance. An observation of the spectral line is trivial without the quantum theory that predicts and explains it. His closest philosophical ally was arguably the energetic polymath Otto Neurath, with his famous metaphor of science as a ship that must be rebuilt plank by plank on the open sea, championed a coherentist and physicalist view of knowledge. He argued for a unified language of science, grounded in statements about physical objects and events. Frank's conception of meaning resonated powerfully with Neurath's vision. Both saw science as a collective, evolving human enterprise, a system of interlocking propositions that supports itself and is judged by its overall predictive and explanatory power. Frank provided the concrete examples from theoretical physics that gave Neurath's more sociological and programmatic vision its scientific backbone. The culmination of these internal dialogues and the public face of the movement's early consensus was the 1929 manifesto, the scientific conception of the world of the Vienna Circle. Frank was one of its three primary authors, alongside Carnap and Neurath. His intellectual signature is evident throughout the document. It champions empiricism and logical analysis, while artfully avoiding the trap of a simplistic verificationism. It speaks of clarifying traditional philosophical problems by translating them into the language of empirical science, a direct echo of Frank's own work on relativity. The manifesto's treatment of physics, its primary example of a successful science, reflects Frank's nuanced view. It celebrates the way theories like relativity and quantum mechanics achieve meaning through their logical structure and eventual connection to observation, a clear expression of the Verbindungsketten concept. The document successfully projected an image of a unified, formidable intellectual movement, with Frank's contributions lending at the unimpeachable authority of contemporary physics. Frank's influence extended well beyond the circle's internal debates and publications. He served as the primary conduit for these ideas to the broader community of working physicists. His pragmatic framing of logical empiricism made it palatable and useful to scientists who might have been deterred by more abstruse philosophical formulations. Furthermore, his work laid the conceptual groundwork for the next generation of philosophers of science. One can trace a direct lineage from Frank's holistic view of meaning to the later, more liberalized criteria of confirmation and explanation. The work of Karl Hempel, a younger associate of the Circle, is a prime example. Hempel's sophisticated analysis of the logic of confirmation, including his famous paradox of the ravens, and his development of the deductive nomological model of scientific explanation, can be seen as a formal refinement of the core insight Frank championed, that the relationship between theory and evidence is systemic and structural. Frank's insistence on keeping the philosophical analysis of science grounded in its actual practice provided the essential stability that allowed logical empiricism to evolve and mature. His role in the end was to ensure that the philosophy of science remained a philosophy asterisk of the asterisk science. This very principle would become the guiding light for his next great endeavor, succeeding Albert Einstein in part in shaping how a generation would come to understand the universe. Assuming the chair in theoretical physics at the German University in Prague in 1912 was a formidable undertaking. The position was vacated by Albert Einstein, who had spent his 16 months there laying crucial groundwork for his nascent theory of general relativity. For Philipp Frank, Einstein's own recommended successor, this inheritance was twofold. It was an immense honor and an equally immense intellectual burden. The challenge was to cultivate, teach, and defend a body of physics so revolutionary that its mathematical language was still being forged, and its philosophical implications were causing seismic shocks throughout the European intellectual landscape. Prague became the laboratory where Frank would apply the principles of logical empiricism, forged in the cafes of Vienna, to the living, breathing practice of frontier science, shaping how a generation would come to understand the cosmos. The intellectual climate Frank entered was one of profound ferment and confusion. General relativity and the emerging quantum theory were frequently targets of misunderstanding, co-opted by philosophical movements eager to find validation in their counterintuitive conclusions. Idealists saw the observer-dependent results of relativity as proof of the mind's primacy over matter. Vitalists interpreted the indeterminacy of the quantum world as a space for non-physical life forces. For many, the theories were simply opaque, a thicket of bewildering mathematics detached from physical reality. Frank's task, therefore, extended far beyond the blackboard. He had to construct a pedagogical framework that could render these ideas comprehensible while simultaneously inoculating them against philosophical misappropriation. His solution was a masterclass in applied epistemology. Frank's method was one of systematic dissection and clarification. He insisted that understanding of physical theory began with a rigorous analysis of its concepts. For him, the meaning of a term like space, time, or simultaneity was established through what he called chains of connection linking the term back to concrete, observable, and measurable operations. His lectures and writings on relativity would commence with the foundational procedures of physics, the synchronization of clocks with light signals, the measurement of lengths with rigid rods. He demonstrated how Einstein's special theory of relativity emerged as the most direct and economical description of the behavior of these measuring devices in different inertial frames. The Lorentz transformations were presented as the mathematical rules that preserve the form of physical laws, like Maxwell's equations, across these frames. This operationalist grounding was his anchor. When tackling the far more demanding conceptual structure of general relativity, this approach reached its full power. Consider his treatment of the idea of curved spacetime, a concept that continues to vex students and laypeople alike. Frank would guide his audience away from a naive, pictorial image of a bent fabric. He would begin with the mathematical tools themselves, primarily the tensor calculus developed by Gregorio Ricci-Bastro and Tullio Levi-Saviter, which David Hilbert and Felix Klein were instrumental in applying to physics. Frank presented the metric tensor, represented as G sub mu nu, as a collection of 10 functions that elegantly define the geometric relationships, the effective distances, and intervals within a given coordinate system. He then posed a physical problem: how can we describe the motion of a planet or the path of a light ray in a gravitational field using the simplest possible law of motion? The answer, he would show, is that if the components of this metric tensor are allowed to vary from point to point in a way determined by the distribution of mass and energy, then the path of a freely moving object follows the geodesic, the straightest possible line in this variable geometry. This variation in the metric tensor asterisk is asterisk what a physicist means by the curvature of spacetime. The term curvature becomes a powerful and compact descriptor for the structure of the gravitational field itself. Frank's pedagogy demystified the theory by revealing its architecture. The physics resides in the link established by Einstein's field equations between the mass energy tensor T sub mu nu and the geometric Einstein tensor G sub mu nu. The seemingly bizarre conclusion that gravity is geometry was thus reframed as a profound statement about the most efficient and empirically successful way to model gravitational phenomena. It was a choice of language, a powerful mathematical syntax selected for its supreme descriptive and predictive power. His seminars in part became legendary crucibles for this kind of thinking, attracting a brilliant confluence of minds from physics, mathematics, and philosophy. A young Kurt Gödel attended, as did other future luminaries. Perhaps the most consequential attendee was Rudolf Carnap, a leading figure of the Vienna Circle. For Carnap, witnessing Frank's live dissection of physical theory was a transformative experience. It provided a concrete, working model for the philosophical program Carnap was developing. Seeing Frank trace the path from raw sense data through operational definitions to the high-level abstract formalism of tensor equations and back down to predictions about the perihelion shift of Mercury or the bending of starlight gave Carnap a powerful exemplar of the relationship between an empirical evidence base and a theoretical superstructure. Frank's classroom was where the logical empiricist philosophy of science was stress-tested against the most advanced physics of the day. The enduring relevance of this pedagogical model is profound. Frank's emphasis on the conceptual and definitional underpinnings of physics is a direct intellectual ancestor to the modern field of physics education research, or PER. Decades of work in PER have confirmed Frank's core insight that students can become adept at manipulating equations while holding deep-seated misconceptions about the physical concepts the equations represent. The contemporary focus on conceptual inventories and active learning strategies designed to confront these misconceptions echoes Frank's insistence on starting with clear definitions and operational meaning. His work remains a vital touchstone for anyone tasked with teaching the counterintuitive yet powerful ideas of modern physics. During his 26 years in Prague, Philipp Frank did something remarkable. He took one of the most prestigious chairs in theoretical physics and turned it into an engine for conceptual intellectual clarification. He defended Einstein's legacy by making it intelligible, stripping away metaphysical baggage and revealing the lucid, logical core beneath. By grounding the most abstract theories in the concrete world of measurement and observation, he provided generations of students and scholars in Central Europe with a robust and philosophically sophisticated understanding of the new physics. This sustained effort of clarification, of building intellectual defenses for science through lucidity, would prove to be essential training for the immense challenge that lay ahead of the fight to preserve the very ethos of scientific rationalism as the continent descended into an age of unreason. The intellectual ferment of Prague, a city brimming with scientific and philosophical dynamism, provided Philipp Frank with an unparalleled training ground. His years there, marked by deep engagement with Einstein's theories and a commitment to their rigorous explication, shaped his approach to science and its place in society. This dedication to clarity, to exposing the logical architecture underpinning even the most abstract physical concepts, proved to be an invaluable asset as the political landscape of Europe shifted dramatically. The rise of Nazism forced Frank, along with many members of the Vienna Circle, into exile, a displacement that presented a profound challenge how to transplant the project of logical empiricism, a distinctly European intellectual movement, onto the different intellectual terrain of the United States. The problem was far from merely geographical. The Vienna Circle's approach, rooted in a tradition of precise logical analysis and a strong emphasis on the unity of science, needed to find common ground with the prevailing pragmatist tradition in America, a philosophy that emphasized practical consequences and the role of experience in shaping knowledge. This was a challenge of intellectual diplomacy, a delicate balancing act between preserving the core values of logical empiricism and adapting its language and methodologies to resonate with a new audience. Frank, alongside Otto Neurath and Charles W. Morris, rose to this challenge, becoming a central figure in the creation and development of the unity of science movement. Their solution was a remarkable synthesis. Instead of presenting logical empiricism as a rigid, inflexible doctrine, they framed it as a flexible intellectual attitude, one emphasizing a commitment to empirical verification, logical rigor, and a recognition of the inherent fallibility of all knowledge claims. This reframing proved crucial in bridging the gap between the Viennese tradition and American pragmatism. The shared emphasis on experience, on the importance of testing hypotheses through observation and experimentation, created fertile ground for collaboration and mutual understanding. Frank's role in this process was multifaceted. He co-founded the Institute for the Unity of Science in Boston, a crucial hub for promoting the movement's aims. He also served as a driving force behind the International Encyclopedia of Unified Science, a monumental project aimed at presenting a unified view of knowledge across various scientific disciplines. This encyclopedia was not merely a compendium of existing knowledge, it was a deliberate attempt to construct a coherent framework for understanding the world, one that transcended disciplinary boundaries and fostered interdisciplinary collaboration. Frank's own contribution to the Encyclopedia is monograph Foundations of Physics, 1946, offers a compelling case study of his approach. Here, he presents the core tenets of physics, not through the highly formal, logic-heavy language characteristic of the Vienna Circle's earlier work, but through a narrative that emphasizes the interplay between theory and experiment. His careful choice of terminology, his deliberate avoidance of overtly technical jargon, and his emphasis on the practical applications of physics all reflect a conscious effort to resonate with an American audience deeply influenced by the pragmatist tradition. He skillfully navigated the complexities of the subject matter, making it accessible to a broader readership while maintaining the intellectual rigor demanded by logical empiricism. The organization of the International Congresses for the Unity of Science further illustrates Frank's commitment to building a new transatlantic intellectual community. These congresses were not simply academic gatherings, they were strategic initiatives to forge connections between European and American scholars, to foster dialogue and collaboration, and to create a shared intellectual space where the principles of logical empiricism could flourish in a new context. The very act of organizing these events, of bringing together diverse groups of scholars from different backgrounds and philosophical traditions, demonstrates Frank's exceptional diplomatic skills and his unwavering belief in the unifying power of scientific rationalism. Frank's influence extended far beyond the immediate circle of participants in the Unity of Science movement. His lectures and organizational work at Harvard, for example, directly impacted a young Thomas Kuhn, a future giant in the history and philosophy of science. Kuhn himself acknowledged Frank's significant role in shaping his early thinking about the structure of scientific revolutions, showcasing the enduring impact of Frank's work on subsequent generations of scholars. Similarly, the historian of science Gerald Halton, whose work explored the interplay between science and culture, also felt the impact of Frank's intellectual approach, highlighting the broad reach of Frank's influence within the academic landscape. The success of Frank's efforts in establishing the Unity of Science movement should be viewed not just as a testament to his intellectual prowess, but also as a remarkable achievement of intellectual resilience and adaptability. His ability to translate the core values of logical empiricism into a new cultural setting, to build bridges between different philosophical traditions, and to foster a vibrant intellectual community in the face of immense political upheaval underscores his profound legacy as a pivotal figure in the history of science and philosophy. His work serves as a powerful reminder of the importance of intellectual flexibility, of the need to adapt and evolve in order to preserve and promote the values of rational inquiry in a constantly changing world. The next section will explore a further dimension of Frank's legacy, delving into his later work on the relationship between science and society. Frank's engagement with the scientific community extended far beyond the theoretical realm. He possessed a deep understanding of the intricate interplay between scientific advancements and their societal implications. This understanding propelled him to tackle the increasingly apparent chasm separating the scientific community from the broader public, a divide fraught with the potential for misuse of scientific authority for political and ideological ends. The specter of Soviet Lysenkoism, with its politically motivated distortion of genetics and the rise of various pseudoscientific movements, movements in the West served as stark reminders of this danger. The central intellectual problem that occupied Frank's later years, therefore, was this: how might a society responsibly harness the power of science without a thorough comprehension of its methods, inherent limits, and underlying philosophical foundations? Frank's response to this challenge was innovative and far-reaching. He developed a unique approach, a form of sociology of science deeply rooted in the principles of logical empiricism. His methodology involved applying the rigorous standards of critical analysis, typically reserved for evaluating scientific theories themselves, to public pronouncements about science. This represented a significant departure from conventional approaches, demanding a level of scrutiny rarely applied to the broader societal interpretation and application of scientific findings. He advocated for widespread scientific literacy, but not in the sense of mere rote memorization of scientific facts. Instead, he emphasized the cultivation of a genuine scientific attitude, a commitment to evidence-based reasoning, logical consistency, and a resolute rejection of dogma. This emphasis on critical thinking, rather than simple knowledge acquisition, proved to be a cornerstone of his approach. A prime example of Frank's unique methodology is revealed in his 1947 work, Einstein, His Life in Times. This book transcends the typical biographical format. It functions as a profound case study in the sociology of knowledge, meticulously documenting how Einstein's revolutionary theories were subject to distortion, mythologization, and appropriation by various political and philosophical factions. Frank's detailed analysis exposes the ways in which these interpretations frequently diverged from the scientific realities, highlighting the dangers inherent in the uncritical acceptance of simplified or politicized versions of scientific concepts. The book serves as a powerful illustration of the disconnect between scientific progress and public understanding, a disconnect Frank dedicated his later career to bridging. This meticulous examination of the societal reception of Einstein's work is a testament to Frank's commitment to understanding the complex relationship between scientific discovery and its cultural context. Further solidifying his commitment to this area of study is Modern Science and Its Philosophy, a work that directly confronts the ethical and social responsibilities inherent in the pursuit and dissemination of scientific knowledge. Here, Frank expands upon his earlier insights, providing a comprehensive framework for understanding the intricate relationship between science and society. He meticulously details the potential pitfalls of allowing scientific authority to be wielded without careful consideration of its limitations and potential for misuse. The work serves as a crucial guide, offering practical strategies for fostering a more responsible and informed relationship between scientific communities and the public at large. His emphasis on the importance of understanding the process of scientific inquiry, rather than simply its results, remains remarkably relevant in our current information-saturated world. Frank's legacy extends far beyond his contributions to physics and philosophy of science. He stands as a singular figure, a vital intellectual bridge builder. He connected the physics of Einstein with the philosophy of Mach, demonstrating a remarkable ability to synthesize seemingly disparate intellectual traditions. He also forged a strong link between the rigorous logical empiricism of the Vienna Circle and the pragmatic spirit of American intellectual life, showcasing his adaptability and intellectual versatility. Perhaps his most enduring contribution, however, lies in his efforts to connect the often isolated world of the scientific laboratory with the complex and frequently irrational dynamics of the public sphere. His life's work culminates in a potent and enduring warning: the defense of scientific integrity is fundamentally intertwined with the defense of a rational and democratic society. The question he leaves us with: how do we safeguard the authority of evidence in an age characterized by rampant ideology? Remains profoundly relevant in contemporary society. His legacy is not merely a collection of academic achievements, but a persistent challenge, a call to action that demands our continued attention and engagement. It is a challenge that resonates deeply, urging us to confront the complexities of the science-society relationship with the same intellectual rigor and moral commitment that characterized Frank's own remarkable life and career. His example serves as an enduring testament to the power of intellectual engagement and the vital importance of responsible scientific citizenship.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.